far, we have discussed linear equations and the elimination techniques for solving set of linear equations. We have also identified that the idea of vectors can be extended to n-dimensional space, and linear equations may be expressed in terms of inner products of vectors or linear combination of vectors. In this lesson, we'll introduce a more compact notation, that is the matrix notation. I believe all of you are familiar with matrix algebra, so we'll cover this part of your course very quickly. I strongly urge you to revisit your undergraduate text on matrix algebra. Recall this equation from our discussion of Gaussian as well as Gauss-Jordan eliminations. We are not going to solve these equations now. We'll simply see how we can write this set of equation in more compact form. Later on, of course, we'll see that writing in compact form may be helpful for analyzing or solving larger systems of linear equations. The first option is, of course, to express the equation as scalar product of vectors. The notation is not very compact, nevertheless, the expression can connect vector and linear equation, which is, of course, a key concept in linear algebra. We now move toward the option 2 that represents the set of equation as a linear combination of vectors. This idea is the key to develop the concepts of abstract vector space that we will examine later. We can of course simply write the equations as equality of vectors having two components. Such expression can be written in two ways: row form, that is a horizontal format, or column form, that is a vertical format. In linear algebra, the column form is usually more common. We can now clean up this notation by bringing a new type of structure shown as 3, 2, 4, 5, known as matrix. Matrices in general are rectangular arrays of mostly numbers. Here we see the matrix 3, 2, 4, 5 undergoes some sort of multiplication type operation with vector xy and produces vector 3x plus 2y, 4x plus 5y. We denote the matrix 3, 2, 4, 5 as matrix A, xy as column vector x. The product of A and x is of course ax, that is a vector 3x plus 2y, 4x plus 5y, and the vector 5, 9 is denoted by B. The overall system can therefore be written in matrix form as Ax is equal to B. We'll move ahead with this notation for the rest of the course. A matrix is usually described as an array of numbers, and you are quite familiar with such description. Matrices may also be described as a collection of vectors, and we'll slowly familiarize ourselves with this idea. Size of a matrix is given by number of rows cross number of columns. And see here the example of rectangular 2 into 3 and 3 into 2 matrices. In this course, we'll deal with plenty of square matrices like this 3 into 3 matrix. We'll also use many single column or single row matrices known as column vectors and row vectors respectively. In a compact form, a matrix capital A with elements small a's is written as capital A equal to, within third bracket, small aij. If we expand this notation, we get the full matrix, where all the elements are explicitly written. Now that we know how to write matrices, let us see what kind of algebraic operations we can perform with matrices. Matrices, as we understand, are essentially collection of vectors. So the basic operations of vectors should be applicable here too. The fundamental operations are therefore surprisingly simple addition and scalar multiplication. You may wonder what happens to many other matrix operations. Well, all of them, as you will see, may be developed from the basic building blocks, addition and scalar multiplication. Let's explore them carefully. Consider three m by n matrices A, B and C. Don't get nervous about the set theory style notation. Capital M simply denotes matrix and small m cross n shows the matrix size. Now the addition operation is commutative. That means A plus B is equal to B plus A. Addition is also associative. That is, for adding three matrices, the order of addition does not matter. Also, there exists an m by n null matrix such that if we add null matrix with A, we get back the matrix A again. Extending this notion, we see matrix A has its additive inverse minus A, such that when A and minus A are added together, we get the null or zero matrix. Considering the above rules, we propose that matrix A with elements Aij and matrix B with elements Bij may be added together to get a matrix A plus B with elements Aij plus Bij. Please note here, matrices A, B and A plus B all are of same size, m by n. Just like what we did for addition, let us list the rules for scalar multiplication. Consider two m by n matrices A and B and two scalars K and P, which are real numbers. The rules of multiplication are as follows. Multiplication of Kp with A is same as multiplication of K with Pa. Multiplication is also distributive such that K plus P times A is equal to Ka plus Pa, and K times A plus B equals Ka plus Kb. We also have a scalar 1, often called identity, and when 1 is multiplied with A, the product is simply A. Keeping the above rules in mind, we propose that when scalar K is multiplied with matrix A that has the elements Aij, the product will have elements Kaij. That means all elements of the matrix A is multiplied by the same scalar K. We now see that the addition and scalar multiplication rules for matrices are remarkably similar to that of the vectors. We have already equated one matrix with another, but never formally defined equality. Let us define that when two matrices are equal, they must have same size and their corresponding elements must be same. So for A and B to be equal, Aij and Bij must be same for each Ij. We'll now move further and examine the matrix multiplication, but before we do so, we need to refresh our memory on matrix transpose. For matrix A with elements Aij, the transpose At is given by Aj. That means transposing a matrix changes rows into columns and vice versa. So the row 1 of A, being A11, A12 up to A1n, is replaced by A11, A21 up to AM1. Needless to mention, we can transpose AT to get back A again. If A and AT are equal to each other, the matrix A is called symmetric, and if A is negative of AT, we call the matrix A to be antisymmetric or skew-symmetric. We also understand that if A is an m by n matrix, AT would be a n by n matrix. So unless A is a square matrix, A and AT are not of same size. A corollary of this is that only square matrices could be symmetric or antisymmetric. In fact, you can prove that every square matrix may be expressed as the sum of a symmetric and an antisymmetric matrix. Why don't you try to prove it? We'll close our lesson now and we'll take up matrix multiplication as our next topic. Since then, please read the relevant sections from your textbook and solve problems from the same sections. Thank you, and I'll see you in next class.